Hey Matilda baby, I am so glad that you said yes to go to prom with me. This night is going so well and I am having so much fun. Not to mention that this music is super rockin'.
Oh Vince, this is the best night of my life. But do you know what would make it even better?
What baby? Anything for you.
Well, since it is the end of the year and our AP biology class is almost over, I feel like we may forget everything we have learned if we do not talk about what we have learned at random times like this.
You want to talk about AP biology right now? Are you serious? What the heck?
Please, Vince. I would seriously love you forever if we talked about cellular respiration right now.
Okay, Matilda. If that is what you want to do, that is what we will do. How about we both act as the characters in a role play of the cellular respiration processes? This can be Act 1, glycolysis. I will be glucose.
Okay. We can pretend that this dancing room is the cytoplasm of the cell. This is where glycolysis takes place. I will be ATP, which phosphoryzes you into 2 pGals.
Now that I am split into 2 pGals, each part of me will oxidize by NAD. This means that I give up 2 electrons and a hydrogen atom to form NADH.
Oh yes, that is right. And then you receive a phosphate, then forming 2 BPGs.
Groovy. Now that I am in the form of BPGs, I release my phosphate groups to 4 ADPs, creating 4 ATPs and leaving 2 piruvates. Here, you be the ADPs. I am handing you my phosphate groups right now.
So I guess that finishes up the first act of cellular respiration. The cell just finished the process of glycolysis. Good work, Vince. All this AP biology stuff is making me thirsty. Wanna get some punch?
No, there are still 2 more processes to cellular respiration. This is no time for dilly-dallying and getting silly punch. My goodness, woman, who do you think you are? Let's start Act 2, the Krebs cycle.
Sassavras, you are being kind of mean to me right now. Let's just get this over with. This time, the dancing room can act as the matrix inside the mitochondria of the cell. I want to be the star now, so I will be pyruvate.
Okay. I shall be NAD. I will steal 2 of your electrons and 1 of your hydrogens to get reduced to NADH by substrate level phosphorylation. CO2 will be released as a waste product while coenzyme A is added, making you turn into acetyl coenzyme A.
Then CoA leaves when acetate and oxaloacetate combine, turning me into citrate. I will reform to make isocitrate.
There are so many steps in this process.
I know. And there are still more.
Just to simplify things, I will take the role of NAD. I will oxidize you twice in order to produce double the NADH and make you release a carbon dioxide. Now you are a 5-carbon compound.
Now I'll pick up CoA again, allowing ADP and a phosphate group to change to ATP. After that, CoA leaves, and I change to succinate.
I am still a reducing agent, but this time I will be FAD. I will oxidize you, turning myself into FADH2 and making you fumarate. As an added bit of information, it is important to know that later on in electron transfer phosphorylation, which will be Act 3, all of the NADH will be responsible for creating 3 ATPs, while each FADH2 can only create 2 ATPs.
Now that I am fumarate, I am pretty thirsty, so I will gain water. I then become malate. Once again, you, as NAD, will oxidize me, making me turn into my final form, oxaloacetate. This process continues. This is the end of Act 2.
Oh nice, we're cooking with gas here. All right, being the perfect gentleman, I will let you be the star again. This is Act 3, electron transfer phosphorylation. So you will be the ATP synthesis, located on the cristae of the mitochondria, and I will represent the oxidizing agents NADH and FADH2.
Wow, that's a mouthful. Okie dokie, so you will be oxidized and release your electrons.
Quiet, woman, I can speak for myself. So I release my electrons that create a proton gradient strong enough to make a proton motive force.
Yes, and I, the powerful ATP synthase, will harness the energy from this proton motive force to engage in ATP synthesis.
Oxygen will serve as the final electron acceptor, which is reduced in the water.
Well, that is all nice and dandy, and not to be an egg, but where did that glucose in Act 1 come from anyways?
Don't you remember anything from the first semester, Matilda?
In fact, now that I think of it, I believe the glucose came from a process called photosynthesis.
Indeed. Photosynthesis is a two-step process made up of a light-dependent and light-independent pathway. The light-dependent pathway occurs at the thylakoid membrane of the chloroplast, where light energy begins an on-cyclic current of oxidation and reduction reactions along the two electron transfer chains.
Oh yes, and do not forget the photosystems, which in the presence of hydrogen, protons and electrons from water are returned to their ground state while a proton gradient builds within the thylakoid interior that is strong enough to power the ATP synthase.
So that means that ATP is created, right?
Well, that is what typically happens at an ATP synthase, Vince.
All right. No need to be sassy. You forgot that NADPH is also made, which along with the ATP, is used to reduce CO2 in the Calvin-Benson cycle, the light-independent reaction.
Yes, and when combined with RUBP, the CO2 is reduced to PGA, and then PGAL by the NADPH and ATP. This is what creates simple sugars such as glucose.
Okay, that is enough AP biology for one night. Are you happy now? We can go get that punch now, and then get our funky on.